Okay, welcome everyone. It's quite overwhelming to see that all of you are here with in such big numbers. Imagine that you would be all sitting in the auditorium at the TU Delft with a cheering audience around you. But today we will do it differently. Today you can make yourself comfortable at home. You can, you can relax in your living room, in the train, or wherever you are. And today we have the honor to receive George van Hal here in the studio and to receive Robbert Dijkgraaf in the US in Princeton. My name is Hilde den Boer and I am the president of the Symposium Committee. And tonight I will be opening and closing this symposium. Thank you for joining us for the last lecture of the 2020Physion Symposium. Last week we've had 4 interesting lunch lectures about the power windows, about creating your own vision, about observing the universe, and about the energy transition. And tonight we've got 2 more interesting presentations for you. Professor Robbert Dijkgraaf will share his vision with us and show his vision about the future of science. But first, George van Hal will open the evening. George is a scientific journalist and he's writing for the Volkskrant. And he will take us with him into the world of science fiction. And he will discuss the theoretical physics of innovations that were done in science fiction movies, like Time Machines, Warp Drives, and the tablet. At the end of the lecture, there will be room for discussion. So please don't hesitate to ask your questions in the Zoom chat. And there will be a short break of 10 minutes in the middle of the lecture, and we will finish the lecture by 10:15. Please note that the lecture will be recorded, but only your voice will be recorded and not your video. So feel free to leave your video on if you wish. Without further ado, please welcome George van Hal.
Hi, good evening, everyone. Thanks for logging in and taking a look at this digital presentation. Like Hilde said, I'll be introducing the theme of this evening, visions for the future, or to be more exact, the future of physics. If you think about the future of physics in a general sense, this is probably, if you have a physics background, which all of you do, this is probably what you'll be thinking about. You'll be thinking about the standard model of particle physics, and maybe some point in the future we'll be discovering physics beyond this standard model, which is definitely very interesting. Or you'll be thinking about the question of whether we will ever manage to glue general relativity and quantum physics together into one ultimate theory of everything. Or maybe you're thinking about black holes and the fact that we don't really actually know what happens to our laws of reality on the inside of these monstrous cosmic beasts. These are all very relevant and interesting questions, which I'll definitely be writing about in the Volkskrant for decades to come, probably. But what I think about when I think about the future is science fiction. And to me, science fiction is not just a hobby or an interesting thing. It's also a very important genre. I wrote a book about science fiction and science in 2015 called Robots, Aliens, and Popcorn. And one of the reasons that I wrote this book is because science and science fiction, they constantly influence each other. And I'm going to give you a couple of examples of the way that happens. For instance, this is the moon landing, 1969, a momentous occasion because it was the first time that we as humanity set foot on another heavenly body, not just the Earth. And long before we actually did this in reality, we were doing it in stories, in books, and in science fiction movies. This, for instance, is 19 years before the moon landing actually happened. It's a movie called Destination Moon. And the scene that you see here before you is basically the same as what ended up happening almost 20 years later. Obviously, there are a couple of differences. The spacesuits are a lot more colorful than what they ended up being in reality. But it's basically the same thing. Someone walks down a ladder, sets foot on the moon for the first time. And this science fiction aspect was actually one of the considerations for doing this moon landing with people and not just with robots or with other unmanned vehicles. Another example, this is 1 year before the moon landing. the science fiction classic 2001, The Space Odyssey. And if you look at this picture with modern eyes, this is an astronaut or a person looking at a tablet computer. Of course, it was just in 2010 that the first generation iPad actually became available. And this movie, 2001, A Space Odyssey, actually fulfilled a role in lawsuits between Samsung and Apple, because Samsung said, well, Apple didn't really imagine this gadget for the first time. It turned up in science fiction movies like 2001, A Space Odyssey, long before they came to market with their technology. So that's just two examples. But if you take a look at the kind of science fiction themes where physics really plays an important role, one of the major themes where that happens is space travel. Space, like they say in Star Trek, is the final frontier. It's the last place that we haven't really left our mark as humanity. And lots of people, especially science fiction writers, want to see that happen. This is the major problem. If you want to go into space, the fact that the universe is really very, very big, it's humongously enormous. And most of you obviously realize this, but this is the main reason that it's so difficult to make science fiction futures like in Star Trek a reality. And this is then, in some sense, our enemy. It's the speed of light, as most of you have probably noticed. The absolute maximum speed in the universe. You can't go faster than this. So the way that we solve these things in regular life, if you want to go to New York instead of Amsterdam, you hop on a plane because the plane is simply faster. It brings you to your location faster. That's not a way to solve this problem of cosmic distances. So this is why science fiction, and especially this type of science fiction, always turns to physics or theoretical physics. And it always comes down to the ideas of this man, of Albert Einstein, and his theory of general relativity. Now, as most of you know, Einstein was not the first, but one of the first to describe our reality in 4 dimensions, dimensions of space and dimensions of time. And usually this is where I start explaining this in lectures for the general public, but I'll assume that most of you are familiar with this, with this theory. And the most important thing for space travel that this theory gives us is time dilation. Because if you use time dilation, you can get anywhere as fast as you'd like. And that's a definite bonus. But there's also a big downside. It doesn't do anything for those who stay behind. And I try to make that a bit more concrete by giving you a quick example with some numbers, which we're all more comfortable with usually than words. So suppose you've got a spaceship accelerating at 1g, which is the same acceleration that the Earth pulls us down with. So it's comfortable to be on such a spaceship. Let's suppose we've got one of those. And then we try to travel to Proxima Centauri, which is 4.2 light years from Earth. In our rocket, it just takes us 3.3 years to get there if you do the calculation assuming that you break halfway so that you can leave your spaceship if you get to your destination. That's a bit faster. That's already pretty interesting. But it gets more interesting the farther away you get. The Horsehead Nebula, 550 light years away. You can do that in within a human life. That's more interesting, right? The center of the Milky Way, 22,000 light years from Earth. You can do that in less than 30 years. Andromeda, same thing. If you have a spaceship which accelerates at 1g and you go to Andromeda and then you go back and you leave sometime in your teens, let's say, you'll get back before you die. So you can do that within one human life in such a spaceship. But then, of course, back on Earth, 5 million years will have passed and everyone you know will have died, as well as our planet, because it will have been swallowed by our sun. So it's not the best idea if you value your social life. This also means that lots of things that we see in science fiction movies are practically impossible, or at least very improbable. Let's take Star Wars, for instance. If you're looking to have a drink with these guys that you see in the screen right here, and let's assume that is on Tatooine, there's a bit of a problem. Let's assume that you try to pay by PIN or a galactic equivalent of PIN. And the bank that you use to do your financial transactions is on Coruscant, which is the Empire's central planet. I looked this up in a Star Wars encyclopedia, and it's a distance of 69,000 light years. So once you tag in your PIN number and you order a beer and you're waiting for your transaction to clear, it takes 69,000 years to go to Coruscant, and then it takes 69,000 years to go back. Of course, for light, this will happen in no time at all, because for light, relatively speaking, the time has been stopped. But that's not a very practical solution, right? So this doesn't work. And that means that in science fiction, we don't actually want to move fast, but we need to shorten the distance. And there's two ways that science fiction movies solve that problem. The first one we see in Star Trek, not Star Wars. It's the warp drive. And spaceships in Star Trek use that engine to shorten the distance, to warp space so that you have a shorter distance to cross. And the interesting thing is that this man is called Miguel Alcubierre. He was working in general relativity. He was doing his PhD, and he was watching an episode of Star Trek: The Next Generation, and he instantly realized, wait, this can actually happen in general relativity. And he took up a notepad, he started doing some calculations, and he actually came up with a way to make this real. This is his publication, 1994, The Warp Drive, Hyperfast Travel Within General Relativity, in a serious scientific journal. Of course, there's all kinds of practical problems if you want to make this a reality, so we won't have warp drives tomorrow. But this gives us a physically probable reason to dream that that might be possible in the future. Here's another example. The story starts with this man, Carl Sagan, a well-known astronomer who sadly passed away. He also wrote a science fiction novel called Contact. And he needed a way to move his main character across a vast cosmic distance. And he asked one of his friends for help. And the solution that this friend came up with was this, a wormhole. Now this person, Kip Thorne, he was not the first person to think up the wormhole, but he did kind of reintroduce it into the field of physics. And for those who don't know, this is the basic principle of a wormhole. Of course, this is not a very accurate picture, but you bend space and time and you create a shortcut, thus shortening the distance, which was our goal for space travel and faster space communication. Now, this is Kip Thorne himself, because he also ended up working on a science fiction movie of his own. Here he is writing down equations on a blackboard, because there's some kind of unwritten Hollywood rule that if you have a physicist in your movie, there needs to be at least one scene where he or she is in front of a huge blackboard with very complicated looking equations. And that's what Kip Thorne is doing here for the character that you see in the front. Of course, the movie that we're talking about is Interstellar, and he did the first version of the script for that movie. And this is what the wormhole looks like in his movie, and it's actually thus far the only movie where this happens, because the wormhole is a sphere. Obviously, if you cut a hole into four-dimensional space, the opening will be three-dimensional, a sphere, and not a round circle like you see in most science fiction movies. And there's other examples as well. Time travel, for instance. We can move forward in time. That's relatively easy. If you travel to Andromeda and you travel back, you've traveled into the future a couple of million years. But traveling back in time, that's extremely difficult and might be impossible. But it might also not be. This is just one of a couple of scientific papers that discuss the highly theoretical probability of this happening. And here in the title, for those who know their science fiction, you can see that science fiction again was the inspiration for this paper in this journal. Because if you take the first letters and you place them together, you get TARDIS, which is the spaceship in the British science fiction series Doctor Who. Okay, so if we're talking about visions of our future, visions in science fiction, I basically think that physics seems to be the key. So most of you have done the best choice a couple of years back when you chose to study physics, and you might be the ones in a future generation or in the future of this generation to make some of these things a bit closer to reality. Okay, that's what I wanted to tell you guys. but I'm not the main attraction this evening. The main attraction this evening is our main guest, Robbert Dijkgraaf in the United States. I'll give the floor over to him in just a short moment. Like Hilde said, if you have questions for Robbert or for me, you can set that, or you can type them in on the Zoom chat. We'll take a look and we'll select your questions after Robbert Dijkgraaf has finished his lecture. There'll also be a 10-minute intermission after Robbert finishes, so we have some time to select the best questions. Okay, that's it for me. I'll give the floor over to Robbert.
Thank you so much, George. And it's a pleasure with this introduction to share my visions of the future of science, in fact. And let me start by sharing my screen. And I hope it's all kind of working. There we go. There we are. So it's a great pleasure to join you all. I know it's very unfortunate I cannot be there in person, but on the other hand, you know, it's a wonderful opportunity to directly hear from my office here at the Institute for Advanced Study in Princeton to be with you. And it was so nice, George, that you ended talking about wormholes, because you know one of the most exciting things that has been happening here on our campus in the last few months is some kind of breakthrough research in actually producing these kind of wormholes. You know, can the laws of physics produce wormholes? And the answer is yes, it's possible if you have the right kind of matter, but unfortunately it will never be able to shorten the path. It's like a real wormhole that you would drill in the ground. It will only make the time travel longer. So it's, again, a little bit disappointing, but who knows? And we can talk more about that in the Q&A. I want to talk a little bit about the future and by starting in the past. And I want to start in the deep past, namely in a time, in 1939. In 1939, there was a World's Fair here in New York. And the theme of was the world of tomorrow, but actually it was a shared view of what science and technology would bring. Of course, it was also a very troubling time. 1939 was the time where essentially World War II would started. But it was a very interesting show. There were many things that you could see there. For instance, it showed the first television. At that time, there were only a few hundred televisions in the whole world. And the first live broadcast was actually the opening speech by President Roosevelt. There was also a robot. I have a little clip of it.
Electro, come here. And here he comes, ladies and gentlemen, walking up to greet you under his own power.
It was the very first robot, Electro. He could smoke. That was the big attraction. He had a little dog, Sparky, that he could play with, and he could talk by playing gramophone records, the old-fashioned ones, the 78 gramophone records. But the second opening speech was given by Albert Einstein, and Albert Einstein spoke about the future, but it was a very interesting speech. By the way, it was a total disaster because he spoke with a very heavy German accent. And the moment that he kind of pushed the big button to open up the show, all the lights went out, and the New York Times reported the next day that the people left the room disappointed to find something else they could applaud. But it's interesting because there were two topics he didn't talk about: nuclear physics and computers. And both of these topics actually happened at the
Sorry, I accidentally muted.
Yes.
Sorry.
So we were, this is where I am right now, the Institute for Advanced Study. This was Einstein's home. And actually right there, he himself, of course, was doing research in nuclear physics. And just a few weeks later, he would write a famous letter to President Roosevelt, telling him to start the Manhattan Project that actually led to the construction of the first atomic bombs that actually were used in exactly 75 years ago this year. And here is the famous letter of picture of him together with Leo Szilard writing that letter, which actually was in reenactment. They didn't took a picture when actually they were writing the letter the first time. Another thing that this institute was famous of was mathematics, in particular mathematical logic. John von Neumann, Kurt Gödel, Alan Turing were all in Princeton. And John von Neumann somewhere says, during the war, I'm thinking about something much more important than bombs. I'm thinking about computers. And his theory of mathematical logic led him to build essentially the first modern computer, the von Neumann architecture, where you have a computer and separately you have basically a memory in which you store the instructions. And here is von Neumann with Robert Oppenheimer sitting right now in what used to be von Neumann's office, opening this machine. It was a huge machine, but it had there was no history at this place. As somebody wrote, the only tangible assets we had were books, brains, prestige, and high hopes, and of course the vision of von Neumann. In fact, that was a computer that only had a 32 by 32-bit memory, so less than 1 kilobyte. But he used that, and he built it actually of war surplus material. And but he immediately started to do other things than calculations of bombs. He started to use it for weather forecast. I like to joke that the first weather forecast was actually made at IIS, and those days it took 2 days to predict tomorrow weather. So it was actually a post-diction. But then very soon von Neumann gets this down to 8 hours, and I find it very interesting. In 1955, he writes about whether we as a human species can survive technology. And you might think this is at the height of the Cold War. This will all be about nuclear arms, but it isn't. He writes actually about climate change. And he writes that climate change will merge the nation's affairs more thoroughly than the threat of nuclear war. And he also has advice how to deal with these future threats, and quite, I would say, stimulating for all of us. He says that in the end, the problems of the future of humanity cannot be resolved by a single prescription, but reliance on day-to-day measures and human qualities like patience, flexibility, and perhaps foremost, intelligence. Now, if we look at the future, I often have this image of these old maps. Now, these are the maps that people made in the days that most of the Earth was unknown. There were blank spots on the map. In terms of my own field, the physics would be the part that is mapped out. And then there are all these parts that we do not understand. And these old cartographers, they didn't dare to leave empty space on the map. And what they did, they painted and drawn these sea monsters, these horrible creatures that would swallow ships. And I think, these days we have sea monsters, which is the unknown physics or the unknown science. So in fundamental physics, we are looking for new particles and forces. We know there's dark matter out there in the universe. We know the universe is largely filled with dark energies. And these are beautiful names, but we have to be honest. We have no idea what that kind of new physics is. And I often joke, as a physicist, you can be very proud that you know exactly what you don't know. We have measured the weight of the universe and all the known matter and forces and everything that you learn in your physics courses, everything that the Earth and we and the stars and the planets are made of, accounts for only 5% of the full content of the universe. So 95% we know we don't know. And often I go to people in other fields and ask them, what's your percentage of dark matter? And honestly, I think, in most other disciplines, the percentage of dark matter is much larger. I think 5% is a tremendous achievement. And, that's so exciting. And I think actually, physics is making rapid progress in understanding more of the universe. And a good example, and George already mentioned it, is black holes. Black holes are kind of these fascinating objects that, say 30, 40 years ago, you would see mostly in science fiction movies. But, they have been responsible for two events that really brought physics on the front page, I would say, of every newspaper in the world. The first one was the detection. So we were all around on the 14th of September in 2015 when the LIGO laboratory measured the first detection of gravitational waves. It was almost 100 years up to the day that Einstein first formulated his general theory of relativity. And the thing they measured was a collision of two black holes that actually were more than 1 billion light years away and produced an explosion that for a brief time released more energy than the whole physical universe that we can observe. So that was a front page. Another front page was just 2 years ago. You saw the picture already, the picture of the black hole horizon taken by the Event Horizon Telescope. That happened on the 10th of April in 2019. There was another, every newspaper I saw actually had that particular picture on the front page. And that's very special. I think, science is in general in the good news department. It was something that cheered everybody up. And again, it was a black hole in a galaxy very far away, M87. So black holes were in the news again, 2 weeks ago. And of course, the Nobel Prize in Physics was announced to two astrophysicists who measure very carefully the movement of stars around a supermassive black hole in our own galaxy. You see the animation on the right, but also to the mathematician or mathematical physicist Roger Penrose, who together, I must say, with Stephen Hawking, made the first major step beyond Einstein's theory of general relativity by mathematically proving that black holes are an unavoidable consequence of Einstein's theory. And in fact, they also proved that the Big Bang was unavoidable. I must say it was a little bit of a sad day because this would have been the day that Stephen Hawking would have received the Nobel Prize. And as you know, he passed away in 2018 on the very birthday of Albert Einstein. So I feel the Nobel Committee could have waited less than almost 60 years. Now, I briefly discussed, particles, the universe, but actually I want to talk to you about this kind of difficult part in the middle, where, our lives are, where our society is, and where great complexity is. And actually, what can science say about this? And this also comes to the question of what is technology? And there are many definitions that I like. I like this one. It's, technology is everything that was discovered after you were born. Certainly my children think of Wi-Fi as like running water or electricity. Everything that doesn't work, by definition, technology has hiccups. But of course, it's the dominant force that shapes and changes both nature and culture. And very important, it's already here. Now, the future is already here in, at your university, here in the minds and the laboratories of scientists and engineers. And I would say, in some sense, the things that we are going to discover in this century are extremely exciting and are much more than we realize. And let me make this clear with a little metaphor. So these are two toy cars, one made of metal and one out of Lego blocks. So what happens if you give these two toys to children and you come back after a few weeks? Well, the Lego will be undoubtedly no longer a car because made into a plane or something else. My main point is that in the 20th century, we discovered the building blocks of reality. Now we're actually starting to build with these building blocks. So this image of nature as this map with blank spots, the sea monsters, the things that we know we don't know that we're going to discover, is only a tiny bit because the real discoveries are not to be found in nature. They are found in everything that we can possibly make out of nature. Most constructions, most configurations of matter and energy have not yet been produced by the universe. Evolution, cosmic evolution, biological evolution, is an extremely slow process. And, so if we look at these building blocks, like the building blocks of life, genes and molecules, or matter, the atoms and the particles, or information, the bits and codes and algorithms. Right now, in 2020, we're living in a time where we start to find the mechanisms to really build the Lego toys ourselves. So we come to it, we have genetic editing in the life sciences. We have quantum technology, designer materials in physics and material science. And we have AI and neural nets and deep learning in information technology. And let me go through these three fields very quickly, because now they're in some sense very, very similar. So again, a little history lesson. It was a long time ago that DNA was discovered, only in 1953. And it took a long time for this to become a regular thing in the life sciences. So there was these like 3 billion letters in a single DNA, 20,000 genes. It took 60 years to discover it, to decode it, to read it, to understand it, and now to rewrite our DNA. So the full reconstruction of the human genome only happened 20 years ago. It took 10 years and almost $3 billion. Nowadays, you can analyze a full human genome, in less than an hour, and for just a few $100s. We have this kind of molecular image of life. We can reconstruct really atom by atom and molecule by molecule what happens in our bodies in living organisms. And we are living in this age of big data in the life science, not only the genome, but also how it's expressed, the proteins, all the chemical processes in our body, the genome of our microbes, all of it is there. And so life sciences became like a very data-driven and quantitative field. Just to give an idea, I find this still astonishing. The full information of the internet right now can fit into 1 gram of DNA. So life is an incredible, efficient and powerful storage and user of information. Now, as I said, the great advantage is the gene editing tool, CRISPR-Cas, and it was in the news again because the Nobel Prize in Chemistry that was awarded 2 weeks ago to Emmanuel Charpentier and Jennifer Doudna, who actually found this breakthrough technology only in 2012. And so we think that sometimes takes a long time for breakthrough science to actually have an impact in real life. They were actually surprised how fast that development goes. CRISPR is now used in many ways, building medicine by engineering materials, in gene therapy. In fact, it's very, very important currently in the COVID crisis. So the route from our brains and our labs to the real world is going faster too. We are building essentially wormholes to apply our technology. In physics too, now there's this famous lecture of Richard Feynman in 1959, where he speaks about there's plenty of room at the bottom. He says there's no principle of physics that speaks against the possibility of maneuvering things atom by atom. We could in principle build the world atom by atom using our machines. And we are doing this essentially. If you think about the chip that's in my iPhone, I have an iPhone 11. It has a bionic chip with 8.5 billion transistors just on this little piece, which is more than the total human population on planet Earth. Now, I always love this little movie. Let me just show it to you. It's made by IBM. They call it the world's smallest movie. It's made by each image, each dot here, each pixel is an individual gold atom. So the whole thing is only like 30 by 30 atoms big. And why are people doing this? They simply do it because they can do it. This has like total zero use, but it's very exciting that's possible. And in fact, this topic and the previous topic are really flowing together. We're living in a time where in some sense we are using the technology of nature itself. Nature, life engineers mechanisms, engines, structures at the molecular level. And we are doing this right now. And this is happening right now, and this only now. In fact, I would say we're going one step further. We're also entering the quantum domain. Now, when quantum mechanics was discovered, say 100 years ago, it was something very exotic. It was just something that, you know, highbrow theoretical physicists worried about. And it was about philosophical paradoxes. But now it's a tool. It's estimated that 30% of the economy is based on quantum mechanics. I would say 100% of reality is based on quantum mechanics. But we are living at the moment when the tool of nature that builds particles, that tool is liberated. And now we as human beings can structure the world just as nature does, at the same scales and with the same power. Now, the expression in English, I think, is bringing cokes to Newcastle. In Dutch, we say bring water to the sea. I'm bringing quantum information to Delft, which is now one of the world centers. I think you all have been brainwashed that qubits, the quantum bits of information, are much more powerful than bits. If I talk to a general audience, they say, well, it's like going from a switch to a dimmer, something that you can rotate continuously between 0 and 1 and on and off. And you know, the great thing of using quantum mechanics is that you can do many things at the same time. We all know about Schrödinger's cat. That's, you know, both alive and dead. That's in a superposition of states. And I love this wonderful animation that actually came out of the QTech lab in Delft, which is clearly, you know, one of the absolute world centers in doing this. That illustrates it very nicely. It says, you know, if you have to find your way in a maze, you know, you would typically, you know, in a classical world, in a classical computer, you would try all the different possibilities one by one. But in quantum mechanics, we have the principle, what Feynman called the sum over histories. You can probe all possible pathways at the same time if you, in a clever way, can keep track of all these different components. If you can keep your macroscopic world, your quantum computer, in a quantum superposition. Well, now we can do this currently. Cutting edge quantum computers have roughly 50 qubits. They are messy, they're not clean, but you know, it's very nice that, you know, whenever you add 1 qubit to a computer, you double the power. So, you know, with the virus, we're all aware of exponential functions. Exponential functions are a great threat, but exponential functions technology are a tremendous tool that allows us to solve very difficult problems. So, you know, most problems grow exponentially. If you add more degrees of freedom, then actually, like, it becomes exponentially difficult to do. And a classical computer will run out of time, even if you have the whole age of the universe to wait. But quantum computers can kind of counter that exponential using the exponential that's built into quantum mechanics itself, and so make exponential problems polynomial again. So last year we had a terrific breakthrough. There was a long debate. Could quantum computers exist? Well, the team of Google at Santa Barbara settled it by just building a quantum computer and make it solve a problem in 200 seconds that a classical computer would take at least 10,000 years. Now, again, this problem is a little bit like my smallest movie. It was a nonsense problem. It was made for the quantum computer to solve it. But I often say, no, it's like if you'll have children, you at some point realize that, you know, at one point, everything you can do better than they can do. But then certainly you're playing a game of soccer and they are obviously better at soccer and you feel, wow, you know, I'm starting to feel old. So I would say last year, the classical computers start to feel old, because if you beat once, you will be beaten more. A third, I would say, component, as I already said, is the information science, which is, I would say, equally exciting. So we have genetic engineering, we have quantum technology, and we have essentially AI. Now, again, this has a long path, though I always love this particular image. It's an image by the father, the Einstein of information technology, Claude Shannon, who kind of makes this kind of list of possible devices and sizes of information. And the biggest thing he could think of was the Library of Congress. And wonderfully, you know, he writes in that list also at 100,000 bits, the genetic constitution of man. Now we know it's 3 billion. So he was wrong by a factor of 30,000. But, you know, it's very interesting. He was the first to start thinking about everything as information. And these days, you know, indeed, everything is information. And we have this terrific collision of a wave of big data growing, you know, extremely rapidly. You know, the amount of data in the world roughly doubles every 2 years, but the amount of data in the life sciences doubles every 6 months. That's pretty amazing. That means that everything we know in the life sciences, 75% of it, is coming from the last year. And computers are struggling to ride that wave of big data. And but your computers love big data, and it's this combination that's actually very powerful. And here's where AI comes in. Now, perhaps you know about the thing called Moravec's paradox. And it says, you know, the things that are easy for us are difficult for computers, and the things that are hard for us are easy for computers. So it's very difficult for me to multiply two numbers of 1,000 digits. It's a very trivial task of a computer. But actually running around and playing soccer is very difficult for computers. And that's because computers think very differently than human beings. Now, computers think in terms of algorithms. They are programmed. They have certain advantages. They never sleep. They have no complaints. And they have an open architecture. It's very easy to add a printer or a second screen to a computer. Very difficult to expand your memory or connect a printer to your brain. But humans have other advantages. Now, we are three-dimensional structures. Our brains are neural networks. We're shaped by evolution. And most important, we are adaptive. We learn every day. We are self-learning mechanisms. And I think this is something that we have seen now. AI, computers based on these kind of neural nets are terrific. And I just want to share with you this little moment. This was the moment where a computer made by DeepMind, which is now owned by Alphabet, by Google, the computer's AlphaGo, beats the world champion at Go. And this happened, it was a famous moment. People thought he was never able to do so. And it happened, I want to show you this little clip. So this is a move that happened in game 2. I think they played 5 games. And it's move number 37. And the computer puts its piece here on the 5th row. Now, there is even a proverb, a saying, I think in Japanese, that, in the beginning of Go, you never put a place beyond the 4th row. This basically tells you, don't go outside the beaten path. You know what you should not do. And the computer did this. And so everybody thought he would make a mistake. And I want, these Go games were live reported on television. And let me show you a little clip of what happened.
That's a very surprising move.
I thought it was a mistake.
Well, I thought it was a quick miss, but
a click. If we're in online Go, we call it a clicko.
Yeah, it's a very strange.
We call it a clicko. You accidentally click on a piece, and now you have to move it. So we thought, oh, okay, that's interesting. The computer makes a childish mistake, something that every beginning Go player knows and has been told to never do. And so the game moved on, and then it moved, and somewhere around move 100, the game came back to that particular place. And what turns out, that this black piece was perfectly positioned to beat the human. The computer was playing with black. The world champion, many times world champion, was playing with white, and he was defeated. And people said, well, these kind of moves, Go has been played for 4,000 years. These kind of move happens only every few centuries, and they call them cosmic moves. It's like an absolute brilliant. It's like writing a Mozart symphony or an Einstein equation. And so it's very exciting that the computer was actually able, the AI algorithm, was able to do something that is brilliant, that's very creative. And I asked the founder of DeepMind, who is a good player himself, how would you describe the style of this algorithm? And he said, well, the algorithm plays like a teenager. It takes much bigger risks. It's in some sense more creative. It knows that it dares to lose, but it also makes pretty brilliant winning moves. Now, you all know AI and machine learning is now all around us. It's being used for all kind of technology in health science and handwriting. In fact, again, in this COVID crisis, AI algorithms have been helping to shape possible, antibodies to go through lots of various kinds of therapies. So, it's really a tool that's being used. And so I would say, AI is like perfectly suited to deal with this gigantic amount of data. And so also in physics, if we want to map out what are future materials, how can we how can we arrange atoms and molecules? We can do this in our lab, but we can also do this in digital simulations, and AI algorithms might be some way to find mathematical structures and laws in this great complexity. We human beings are not able to think in very complex systems. If there's too much data, we get a headache. But these algorithms are able to, they actually enjoy, they love huge amount of data. They grow by it, they enjoy it, and they make very creative solutions. And so, but it also raises very deep questions. What problems will be arranged, can be addressed? What kind of solutions can we find? How robust are these results? It's one thing if you play a game of Go and you lose once, but if you are a self-driving car, you don't want the car to suddenly become kind of very creative and go off the road. How do these insights generalize? And if the algorithm understands it, can we human beings understand what's going on? And I love this series in the Wall Street Journal that actually is called Careers of the Future. And one segment was about robot psychologists. And so this is not about a robot being a psychologist. No, it's about a psychologist analyzing a robot. Because if you have these very advanced structures, these very advanced algorithms that we don't really can understand, and we cannot look inside the algorithm in the same way I cannot look inside your brain and see from your neurons and neural nets how you're feeling, whether you're depressed or whether you feel great. The only
Sorry, I accidentally clicked something.
Okay, let me go back if I can. Yeah. Oops, there I go. The only way to analyze whether these systems are behaving well is probably like put them on the sofa and ask them questions. How are you feeling? Or let them talk about their internal state and so figure out and learn from them. And so our conversations with these algorithms could be very similar to the conversations that we have with each other, where we tell each other what we think, how we feel, etc. So I think this is all very exciting. And in fact, it's even more exciting because it's this triple helix. Uncovering the secrets of life, using the technology of quantum theories ourselves, using the artificial intelligence and other insights that modern computers bring. That's all kind of feed back into each other, and it's accelerating, and that's extremely exciting. But I must say it's also worrying because it goes fast. We have an exponential growth in technology, in data, in how smart these machines are. And that also gives a different image of our relation, I want to end with that, with science and society. So it used to be that science happened in the laboratory, in your studies. Society wasn't really impacted by it, and there was a very clean dividing line between it. Now, I think what's happening with all these new technologies is that science will be everywhere. So it will literally be in your smartphone. It will be in the medicines you take. It will be in the algorithms that determine your life and what you do and what you think. At the same time, science is getting more and more complicated. It's more difficult to understand how things work. Now, who really understands these quantum materials? Who understands what exactly genetic engineering does and what the risks are? And literally, we do not understand how these machine learning algorithms work. By definition, we cannot open the hood and study it. So one thing I'm worried about, which I call the knowledge paradox, that will be in a world where on the one hand, science and physics and research is infinitely far away from the non-experts because it's so difficult to understand. Only a handful of people will fully understand it, perhaps nobody, or only a computer. On the other hand, it's also infinitesimally close because it's everything we do is governed by it and makes use of it. And so if you just take the mathematical limit, you have a all-powerful technology that's completely invisible. And somebody said, coming back to you, George, that if any technologies suitably advanced will look like magic, and people will think about it as that it's magic. So how can we bridge that? Well, I'm happy to discuss that further. But I think that the main lesson I want to say is that if you feel that physics is done, that science is done, you couldn't be more wrong. Because not only are there many things we know we do not understand, but there is even much more to explore. And I almost feel obligated to end with a quote by Albert Einstein. This is not Einstein's office, but he would be in the office next door. So I brought my little Einstein here, and he says hello to all of you. But his favorite quote, my favorite quote of Einstein is this one: "Imagination is more important than knowledge. Knowledge is limited to all we know and understand, while imagination embraces the entire world, stimulating progress, giving birth to evolution." Please be aware. If you open your mind, if you just start to realize what's out there, what an extremely exciting time we live, and how much there is there to be explored. There's no reason for you. There's no apology for not to kind of dive deep into that future and shape that future. And I want to end with really the best thing of my current job. Now, I often joke, if people write to Santa Claus on the North Pole or to Sinterklaas in the Netherlands, I'm not quite sure where these letters end. But sometimes, children write a postcard to Albert Einstein, and they come on my office. So a few years ago, I got this postcard from Shawol. She or he lives in New York. On the other side is actually the Statue of Liberty, and he writes to Albert Einstein, "I hope you will never stop being curious." And I think, I think this must be a 6-year-old, a 7-year-old. I think there's no better way to capture the message that I have for you today. So thank you very much.
Nou, welkom terug allemaal. Een ware explosie van vragen zag ik in de chat. Oh, sorry. I automatically switched over to Dutch. So welcome back, everyone. A true explosion of questions in our chat. I was very happy to see all these interesting questions. Unfortunately, we probably won't even be able to tackle all of them in the next 50 minutes, but we'll try to get as far as possible. One more thing, we'll be handing out a JBL speaker to the person who asked the most interesting question, according to us. But we'll let you know at the end of our session who that was. I think the easiest way to do this is if I mention the person who asked the question, and that person unmutes themselves and they ask the question to Robbert or sometimes to me, but usually to Robbert. And then we let Robbert answer the question. Robbert, if you have any questions that you already saw that you really want to answer, feel free to do the same thing. Otherwise, I have my own selection here right in front of me.
Well, I must say they're really all excellent, and I think already wrote down 30 questions that I would love to answer. So I will be very brief.
Okay, excellent. So I'd like to give the first word to Pim Laven. He had a very interesting question.
Yes, good evening. Hi, Robert. I had a question about the mission to Mars or from Elon Musk. So do you think that as a human kind, we have to basically go to other celestial bodies or other planets in order to make sure we can like persevere in the future? So maybe one day our planet Earth will be out of livable resources. And but do you think Mars would be the best option for this, especially because of the huge dust storms and electrostatic discharges in the planet, for example? That was
I think it's a wonderful question, and one of the great physicists that unfortunately just passed half a year ago was Freeman Dyson here at the Institute, and he had a very strong view. He felt it's our obligation as a human species to spread through the universe. But it's not clear that we actually physically have to do this. You can be a bit more creative. So definitely, I think we should send rockets and satellites and robots. Dyson himself had this idea. You can put the DNA of all possible organisms on the world, in a very small rocket, which he thought something like a Noah's Ark, and you can shoot that out into the big unknown. But I think it's terrific that we are actually exploring this, and it's very exciting these days that it's in some sense partly also people like Elon Musk. It's individual enterprise. It's the commercial interests that are doing so. I think he likes to go to Mars. Some people say, well, if you want to live at Mars, why don't you first build a tent on the top of Mount Everest or something, because it's much more comfortable than Mars. But I actually personally feel at the long term, I think I would be very, very sad if the human species basically retired to planet Earth and wouldn't explore the rest of the cosmos. I feel we need to, and I think we will, because we need only 3 crazy people to do so and make it possible.
Thank you.
Okay, so I'd like to give the word to Jelle. He asked a couple of questions, and I'll let him decide which one he wants to ask most.
Yes, thank you. I think I'll go over the long question then. So I'm studying in nuclear fusion at the moment, and one of the big issues concerning the build of ether and of fusion devices is that they say, well, it might simply be too complex for humans to realize this. And I fully agree on you in terms of talking about the building blocks, that there is so much more to explore in terms of physics and engineering with the things we know at the moment. But in terms of theoretical physics, could it be possible that we're also hitting such a roadblock of complexity that it will simply not be possible anymore to expand on it further with our tiny human brains? And if we, for example, would look into having AI solve these problems for us, would it be desirable to do that and having us losing all intuition over these results?
Well, this is an excellent question, because in some sense, our image of what the breakthrough particularly in physics is, with like finding a particle, finding the single equation that rules the universe. Let's say that's the easy ends of physics. The easy ends are the very small and the very large. By definition, if you zoom out, you only see the larger structures, and if you zoom in, you see only a few bits. So the difficult part is the middle, and this complexity barrier is extremely exciting. And I think so part of my story today was that we are developing the tools to tackle this. The question is, I think big question is there any hidden simplicity in that complexity? And it's not automatically not true. So we know simplicity can come by going to the building blocks, but studying the waves of water is relatively easy compared to studying the movement of 10 to the 24 H2O molecules. So there's always the opportunity that simplicity is be found. Then the question is, how do you find these structures in these infinite dimensional spaces? Where do you find something that you can actually hang on to? And I think actually applications of AI in science could be a terrific way to find these kind of structures. In fact, I would say AI has been very successful exactly in those cases where you have hundreds of thousands of variables, but in some sense you can reduce the problem to a much lower dimensional subspace. Is this the case for, say, turbulence? There was a question about turbulence. Is there a question? I mean, there's so many complexities out there. We don't know, but I think it's terrific that we are not limited by the size of our brains, or even our brains all connected and communicating, through email and through books. study books and articles, but also we have these kind of external hard drives and external computing power. And so I think the future is really human plus machine and the interaction. In some sense, that has been the story. The fact that we can actually understand the smallest particles in the largest structure in the universe is, of course, we were able to build particle detectors that are like 27 kilometers big, or telescopes. Like the picture of the black hole horizon was taken by a telescope that was literally the size of the planet. So we have always been using auxiliary eyes, auxiliary ears, and I think now also auxiliary brains to go further.
Thank you very much. I guess I would agree with you on that. And if I may be so cheeky to ask a very tiny small question in between. So
yes.
as the rector of Princeton, are you actually still involved directly in research?
I am, but it's I have to manage this. I also have to manage the institute here, and so I always joke, I'll try to fail equally in both tasks.
That's good to hear then.
Yeah.
Okay, I'd like to go over to Catherine Xu, who had an interesting follow-up question, I think, to this discussion.
Hi, will computers ever rule over humans? Can you hear me?
Sorry, I missed you. I missed the question.
Oh, okay. Will computers ever rule over humans?
Well, I think the first answer is probably they do already to some extent. We might be slaves to our iPhones, and no, but it's a wonderful question. I noticed there was a whole series of questions about what I would say the lights and shadows of technology. Now, again, I'm here in the office of Robert Oppenheimer. I've put a picture of him in that particular office here on the back, and I always tell the story that when he was sitting here, if you walked into the office, there would be 2 US Marines outside with big guns and a safe that kept America's atomic secret. So clearly, also physics is not only wonderful things, it's actually something you can destroy the world. So I think it's incredibly important that we realize the power of these technologies and think about how they're being used, what we do. In some sense, we always have been very dependent on those technologies. You cannot farm, you cannot build a factory without technologies. But on the other hand, you feel that you should be in some position to make the decisions. And I think by moving in the world of AI, it's tricky. It's tricky. And I think lessons we have learned is that the best way is to have these discussions simultaneous. You shouldn't first develop the technology and then ask the question whether this was okay or not. One issue I do worry about is the rate of progress. The fact that, in a year, the world also of science and of technology has changed so much. And I think our society is very, very bad at adapting fast. In some sense, politicians, they think in terms that, were relevant perhaps 20 years ago, if only that. And so I think this is really an issue. How can we keep the world up to speed and make sure that these decisions are taken in the right way? And I think it's something you can be both worried about and you can be very excited about. I often joke, if you think about this world, you have to be a little bit like Schrödinger's cat. You need almost think about it quantum mechanically, both from a positive and from a negative point of view at the same time.
Thank you.
I'll give the floor to Amanda van Hemert, who has a very different question from the last one.
Hi. I asked, what does it feel like to traverse a wormhole?
Okay, so so it depends as well what kind of wormhole. So the latest wormholes, and this is just something, again, I said you kind of breakthrough research that's happened here in the last few months is that with the right kind of matter, you can make a big wormhole. It will look something like, in some sense, it's almost like a black hole, but it's a black hole without a black hole horizon. So it's something that you would fall into. You would be accelerated. in some, you can perhaps compare it a little bit. You could make a little low-tech wormhole by drilling a big hole like from the Netherlands all the way through New Zealand or something, and and just fall through that big shaft, and you would be accelerating, and in the middle you would be going very fast, and then you will pop up at the other end. I think it takes 45 minutes to travel in this way to the other side of the planet. So I think it would be a little bit like this. I think not the old wormholes there, you would be scrambled and you would essentially, go out in a gas of particles. These traversable black holes, you would actually survive. Unfortunately, you will not end up into the future. You will actually end up older than the future. So it will not have this kind of nice feature that George said. You can boost yourself to a future. In some sense, you will be the last to arrive at the party.
I'm still holding out hope for the
Oh yeah, who knows? This is just with our current understanding.
Okay, so next question goes to Philippa.
Hi. If we begin building larger and larger entangled systems, do you expect that our idea of reality on a macroscopic level will change?
That's an actually beautiful question, because in some sense, our intuition for reality is of course wrong, right? We think in terms of the world as and classical systems, and that's why we discovered classical mechanics before we discovered quantum mechanics. And that's because we have macroscopic objects, and all the intricacy of quantum mechanics, the entanglement, the superpositions do not happen in our everyday life. I think actually we're already moving that direction. The fact that we can make entangled systems that are like kilometers away means that your generation growing up with these systems is already more accustomed. This is something could be inside a machine. I think Niels Bohr would never have thought that he would have a quantum machine on his desk. But I think it will change our nature of reality. Another question that was also raised, and it's a little bit related to it, is quantum mechanics the ultimate statement about reality? Is this the final word? And with all the philosophical problems that go along with it, and Einstein himself had great trouble. I think there isn't really a common understanding. There's not an all-time favorite interpretation of quantum mechanics. There are many conceptual issues, and I would say so. From a theoretical physics point of view, in the end, we know that quantum mechanics has to somehow be unified with general relativity. So I would see, my own intuition is that quantum mechanics is not the final word. There's something more fundamental out of which both quantum mechanics and general relativity will emerge. That's a very astonishing statement. It's like telling mathematicians that numbers are not the ultimate thing. There's something even more fundamental. They would immediately ask, what could be more fundamental? And of course, we physicists ask the same question. But undoubtedly, I think the fact that quantum mechanics will be part of everyday life, I think will change our nature of reality. Yes, I think it will. Certainly, I think we'll be making use of these practical implications of quantum mechanics, and it's wonderful to see that the philosophy of physics is almost making a comeback, because quantum theory is becoming more and more part of our world.
Thank you.
Okay, so I'll give the next question to Niels.
Yes, thank you. I have multiple questions, but I think I start with the most pressing. So before I sound too cynical, like it is a bit of a longer question, but I was listening to Sabine Holzenfelder, and she's, I think, a colleague of yours. Yes. And she criticized that physics has spent so much time and resources in the 20th century on string theory, on finding a theory of everything, even though it's not really following scientific principles. Like, there doesn't have to be the case that there is a single theory of everything. Like, why do the three forces except gravity have to be united, for example? And like, it really has been institutionalized that string theory is the way to go, and like in the end, it turned out string theory is problem after problem and fix and problem, and this has been going on for quite a few years. And how do you think we can like prevent this happening in the future again? That we don't follow the principles of scientific, like that we follow the principle of beauty. Yes.
Let me stop that, because I think, I do appreciate that criticism, but I think it's like fundamentally wrong. And let me tell you a few reasons why. So first of all, I think people think like string theory is just this is one particular theory. And everybody is taking this exit, there are all these other exits that are not explored. I think, right now in theoretical physics, people exploring a whole range of options. In fact, if you go to a string theory conference, it's very rare to actually have an actual talk about string theory. That's little wiggling little pieces of string. So I think the question of combining quantum mechanics and general relativity has to happen, because there's only one universe, and clearly it's operating in a certain way. Something is happening in a black hole. Something happened close after the Big Bang. Something happens if you go to very high energies and very short times and spaces. So there's a whole circle of ideas. I think actually the problem is more that there are many different ideas. They seem to be consistent, but we haven't yet found a ultimate set of working principles. Now, so some of the criticism is, well, progress in physics is not being made by thinking about it. It's by doing experiments. Well, honestly, that's not the case. I think the real progress being made, say, in general relativity, didn't come because people were measuring so carefully the orbits of Mercury. No, Einstein actually thought very deeply about space and time, and then he discovered his equations. In fact, he used mathematics that was extremely advanced. So honestly, if I'm asked, will you ever see the solution of this huge problem of combining the two standing theories of physics? I think, yes, it will happen. It will not happen through an experiment. It will happen through some brilliant insight. Somebody who's able to put her or his brain around this and solve that problem, just as problems in mathematics are being solved. It's a conceptual problem. And then finally, there haven't been any phenomena that are explained by quantum gravity, but the ideas of string theory are being used in the lab all the time. So I saw questions about holography, how the three-dimensional world can be captured by four-dimensional curved spaces. These kind of techniques are being used to understand certain materials. It's to understand things in mathematics, to understand things in heavy ion collisions, very kind of bread and butter physics. So I think it has been extremely successful, and it's almost like you're learning calculus. No, there's no way you can unlearn calculus. No, you can apply it, and it's just a tool in your toolbox. Whether this is the right way to lead us in the end to a final theory, if such a thing exists, we don't know. But I would say there's nothing like the thought police. People are actually exploring a wide range of options, and everybody's free to add to it. And I think it actually is something very, as somebody said, we don't need thought police. We don't need people to tell us what to think and also what not to think.
Okay. Robert, you mentioned the philosophy of science becoming,
yes,
or getting more to the foreground. And I think Wouter asked a really interesting question in that regard.
Yes, so my question is a question that my physics friends and I ask ourselves a lot. And it is the goal of physics, all the work that we're putting in it, to actually discover the real structure of the universe? Or is it that we're just trying to make a perfect model of what we see in the universe? I was wondering what your view on this is.
Yeah, that's a very good question. To what part are we able to capture of the universe using our equations, using our laws, using our ideas? And obviously, it could be that there's a huge part that we don't see, we're not even aware of, that we don't pick up the structures, because you can think your brain is now grown by evolution. It's like we pick up certain signals, so we see certain things. But we have been extremely successful in making predictions of reality. The fact that we collide particles and we predict using our equations the properties of these particles up to 12 decimals. That's pretty exciting, you know. We know it's not a perfect answer, but it's very, very impressive. So I think there's very little evidence at this moment that there's a huge part of reality that is not being able to capture it by science. It could be, of course, it can always be. It's very difficult to know what you don't know. So, but I think, you know, it's, I feel the kind of mathematical models that we're making of the universe seem to be, for my feeling, pretty close to what the universe is. But, you know, it's also perhaps just a personal point of view. I think the proof is whether we are able to really understand what's happening, and are we able to make predictions, and are we able to understand what goes on. But the fact that, you know, somebody puts a microscope and looks at a supermassive black hole, you know, hundreds of million light years away, and the image looks exactly as we calculated, I find that pretty impressive.
Thank you very much.
Okay, let's change tack a bit, and I would like to let Fenna ask her question.
Hello, Mr. Dijkgraaf. Thank you so much for your very interesting presentation. My question was actually because you spoke about the possibility to travel in the future. My question was, do you think that it would maybe be possible to travel back back in time in a parallel universe?
I think there are many components to that question. So this is, you know, well, parallel universe or just our universe. So there's this issue in just studying technically the general relativity. The equations of Einstein are the things that we call closed time-like loops. So you go up in time, you go back in time. And there have been many hypotheses that, you know, the equations forbid these structures to appear. Actually, by, you know, pretty formidable mathematical calculations done here at Princeton University, they found that in the collisions of certain gravitational waves, you can actually make these loops. They actually typically are unstable. So if you perturb them a little bit, they disappear. That's just studying Einstein. The second element is then putting the matter fields on top of this and study these structures. So I think the consensus is these closed time-like loops might exist. They are unstable and they are certainly not traversable. So it's not something that a human being will go through. But I don't think it's totally forbidden and will not appear in Einstein's equations. And, you know, there's something that people are troubled about, because clearly, you know, it has a huge impact of what we mean by, you know, science as something that's progressing into time. So there are serious issues, but I don't think there will be any practical applications of the idea.
Thank you.
Okay, I'd like to move on to Erik Schneider. If you're still there.
I'll take it from mute, that helps. Thank you for your story so far. I have a slightly different question, and it's interesting that your perspective is from the US, because we see quite a lot of people who basically do not believe in science and consider it as just another opinion. Even people in some very important places. How do you think we should deal with that? And that's basically two questions. How should we deal with that on a society level? And what can we do in individual conversations with people like that?
Yeah, so I think, you know, I feel that part of the problem clearly is related to the point I mentioned at the very beginning, at the very end, is that, you know, science become much more important. So I think there are reasons to not believe it, because, you know, if climate scientists say that you have to stop, you know, building certain things, or, you know, stop flying or whatever, you know, that impacts your life. So you will push back. So that will be something that will make it, I think, worse, because clearly scientific issues are becoming politically relevant, and, you know, people have to make difficult decisions. I think it also, one thing that will make it worse is that, you know, science is just very difficult to understand. So it's easy to confuse people. I feel actually that, you know, in our world, in the world of science, we have to spend more time explaining what science is, how it works. that we do experiments, that we observe, that we analyze, that we have uncertainties. I would say the inner working of science. I think perhaps we have put too much emphasis on the results that then are being discredited, and not enough on the whole structure that's behind it. And that means that, in education, we'll not just have to teach people, what the laws of physics are, but also know how can you be a researcher yourself in your everyday life? What does it mean? What is the scientific method? So I think that's important. And I think, in one-to-one conversations, it's good to highlight all the knowledge behind the conclusion. And I think this is something very unfair. I think like the media play an unfair role because you can have somebody representing the scientific consensus, and then you put like a skeptic across the table, and I always say it's always ends in the draw because there are two opinions, and then people say, well, okay, there are two opinions, yes, no, so probably the answer is somewhere in the middle. Well, one is representing the scientific consensus with like perhaps tens of thousands of researchers that spent their whole life. The other person is just not bothered by elementary logic and can say whatever he or she wants. And so it's a very unfair advantage. So I think also the media have to some sense, make sure that they give people the right kind of credit.
Yeah, I'd like to say something about that.
Yeah, please do, because that's your job, George.
Yeah, exactly. There's this famous quote, I forgot who said it, but if you're reporting about the weather and you're trying to answer the question if it's raining or not, you don't need to get two people inside a television studio, one who's saying it's not raining and one who is saying it's raining. It's your job as a journalist to look outside the effing window. That's the quote, and I feel that is our job. But it's very difficult, especially for media who don't have science reporters like the Volkskrant does, for instance, or NRC does. They have large science reporting sections inside their journalistic build, and it's more difficult if you do not have that expertise. So that's one way to solve that problem, to get more science journalists inside.
Well, I must say I really agree with that. I really agree with what you're saying. And if you, George, I would put it almost differently. If you think about, you have the public or you have policymakers and you have the origin of the scientific discovery, there's a big bridge that connects it. And there are many roles. There are people, there were also questions about like you have individual fields. Who is able to synthesize this? Well, it's a separate job. There's another job to somehow articulate how these conclusions were drawn. Now, I at some point was involved with the IPC climate panel, and I noticed that they didn't have a communication department. They just felt if they say, well, it's get 1.5 degrees warming, that's good enough. Well, no, you have to explain it. And I think we need many more people like you, but I think also we need the diversity of journalists who are able to work in different media, some who are more knowledgeable, others who are less perhaps themselves active in the field. And I think that's also, by the way, a call to all of you, because it's not true that all students will have exactly the same jobs. No, I think of what the scientific community in a broad sense is like a big symphony orchestra. And we need all these different instruments to play together. But there are different roles in addressing this issue. And I think it's one of the key issues going forward, because there is a bleak future where we have all the solutions, we have all the answers, but nobody is willing to listen to it.
Yeah. I'd like to give a question to Tessa, who has a more extreme role in her mind for scientists.
Oh.
Oh, yeah. We were talking about politicians who are still thinking in terms 20 years ago, and talking about the fast evolution of the revolution of AI and the all common science. And my question was, should scientists rule the world?
Oh, no, I don't think so. No, certainly, anybody who knows anything about university politics will immediately say no. I think, there's a different job to do so, but I think, it's a little bit like the human and the machine. I think they should all work together. And so one thing I feel that scientists should be more involved in making these policy decisions. We are living now through a pandemic, and we see this almost how we're feeling our way around. This is the first time that I think, ministers, prime ministers, they have to listen very concretely, and they're struggling with it, obviously. So I think this will be a look into the future. I think it will be extremely important, and there's something that you can do. Now, certain countries are further, like for instance, in the United Kingdom, each department, each ministry has a science advisor, and there's a science advisor to the prime minister, and they all work together. So there is some sense an infrastructure on the side of politics that's able to receive that kind of information and deal with it. The Netherlands, we often feel, well, they say, well, every country has its own way. I think actually there are some mechanisms that are better than others. And it's almost if you're a company and you are a tech company, and you know that the future of your company is essentially dependent on your R&D. Like if you're Apple or Google, you make decisions that are very much informed by technology. And it's not that the technologies are running the company, but they listen very carefully. And I think actually our society is becoming more and more like a tech company, in the sense that we are totally dependent on R&D. And that takes a different kind of a mindset, I think. But I think in the end, it's not that the scientists have the wisdom, because actually implementing these ideas and building a society around that. That's something that's much more in the area of the social scientists. Humanists were able to say what this means to be a human being. Now they are in some sense much more accustomed to dealing with very difficult questions, like questions that are almost impossible, like what is a just society? How do we want to create a society that we're all happy in? That's something that physicists typically do not ask themselves. So I think the scientific community in a broad sense can play a very important role, and I think we need to upgrade, so to say, politics with more science, technology, but clearly also the other fields, the social and human sciences.
Okay, thank you.
Okay, we're nearing the end point of tonight. I'd like to give one final question to Jasper Brookman, who has a question that ties in very nicely to the theme of this evening.
Yes, thank you. Good evening or good afternoon. Actually, I asked this before you even showed it, but this ties into the letter to Einstein you received or showed us. Basically, my question was, what are you curious about? What would you like to learn or want to learn in the next few years?
So thank you for asking this question, because I think this is kind of it's a question we should all ask ourselves, and and you should be unashamed to share your dreams. So honestly, my dream is I just want to understand why the world works. I think there is a logic to all of things that we are seeing. I'm actually extremely confident that in the end, the human minds will be able to solve this. But people sometimes ask this question, okay, you're sleeping for a few hundred years and you wake up. What's the first thing that you would like to know? Undoubtedly, there are terrific breakthroughs in everything I told you, but I would immediately look up on Wikipedia theory of everything. I think that would be my first thing. And I would probably be very disappointed. I think that might be. There's a famous quote by the mathematicians David Hilbert, and he was asked that question. He said, if you wake up after 500 years, and he said, I look up the Riemann hypothesis. That's a big theorem in number theory. So I think that's what I'm curious about. But I think there are so many reasons to be curious, honestly, and so I think that's perhaps there were some questions about creativity, about why are we studying physics or any other field? I think, you know, you should be, this curiosity is something that is a great gift. So I often have this image of, you know, you're walking in a mountain landscape and you're wondering, you know, what's behind the other, behind the mountain. You know, you can't see it. And I think we have two tools to do so. The first is our imagination, which is like tunnel vision. It's trying to see what's behind it. I just imagine something, and you know, it could actually be true. I think we are living sometimes in a times of very, very much lack of imagination. And so we can learn from artists, in fact, from the science fiction that George, that you showed, you know, who are really visionary. And so we should stimulate our imagination. But then there's something, the second tool I would say is the curiosity. And the curiosity is just the urge to climb over the mountain and have a look. And I know every child, if there is a wall, the child wants to climb over the wall and see what's there. If there is a sign, don't enter, children all will gather in front of that sign and want to peek what's there. And I think it's a very natural urge. You know, I'm not sure whether it's true, but it's often reported these experiments that they did, whether, you know, whether people were able to think creatively, and there was a test done for NASA astronauts, and only 2% of the candidates to be an astronaut passed the test. And then they gave the same test to 6-year-olds, and then 98% passed. Because, you know, if you're a 6-year-old, you're very eager to go across every possible boundary. And then you grow up and you learn everything, the little things that you're learning now in the university. And you get this feeling, wait a moment, this is a complicated world. I have to be very careful. I can make mistakes. If I make mistakes, I fail my exam. And you become very anxious. And then at some point you start your career or you become a researcher, and then people tell you, be curious and start imagining things again. And then this engine has to start again. And I think the trick is never slow down. Now, even if you're learning more about the world, keep that curious spirit. And, you know, if you can say anything of Einstein, no, he was kind of able to do so. And he did so by, you know, slightly detaching from the world, not trying to agree with everyone, you know, and just keep a kind of a nice distance of objects, because I think that's the way to keep this kind of curiosity. And I think it's a gift we all are born with, but it's something that we are sometimes in our education, we make a lot of efforts to unlearn the curiosity that I think is very native to us.
All right, thank you for your excellent answer.
Yeah, that seems like a great place to end this discussion. I'm taking a look at Hilde, who has some closing remarks. When do you want to announce the winner of the JBL speaker?
Do you have in mind?
I have selected one question.
Yeah, I think now will be a great time.
Okay, I would like to give this JBL speaker to Wouter, who asked the question about model versus reality and what it is that physicists are actually trying to uncover, which I think is a very valuable question to keep asking yourself if you are in the field of physics.
Thank you, Wouter. You can send your telephone number to Willem Rosenbrand in a private Zoom chat.
Okay, I'll give the floor back to you.
Thank you. Thank you, George, for your inspiring words. Thank you, Robert, for your inspiring words. And thanks to all of you for your interesting questions. Yeah, it was such an honor to work together with these impressive speakers. Thank you. Jan, can you put on the PowerPoint, please? Yeah. Thanks to Jan behind the scenes. And to Willem, who was doing the Zoom. And there seemed to be something wrong with the leaving people in from the waiting room and muting Robbert Dijkgraaf. So he was very anxious about that. And I would like to thank the rest of my committee who are watching this from home. Yeah, we've had a wonderful year together. And during this year, Corona kept on limiting us in the symposium, but our flexibility was very great. So we managed to to organize a great symposium. Thank you. And the recording of this lecture will be online on our website, symposium.vvtp.tudelft.nl. Yeah, thank you, audience, for being here today. And hopefully we'll see you next year.